15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again, and thank you for joining us. This is Space Nuts, where we talk astronomy, space science, and all sorts of exciting and interesting things, and a whole bunch of other stuff as well. Coming up in today's program, we will be answering the question as to why comets can have green heads but not green tails. I've always wondered that. Every day it just crosses my mind. I go, why do comets have green heads and not have green tails? It's mystified me. Didn't know it was a problem. Anyway, we'll also be looking at a magnetic field that's been detected on an exoplanet for the first time, and a couple of questions. One from Justin about cryostasis. Will it ever be possible? I certainly hope so. I could use the sleep. And Vinicius, I hope I've pronounced your name correctly, from Brazil, wants to talk about gravitomagnetism as maybe an alternative theory to dark matter. And gravitons as well. Pretty deep discussion, that one. It'll take us probably 4 to 5 hours to knock that over, but we'll get into it later. My name is Andrew Dunkley, your host, and joining me as always is his good self, Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. How are you doing?
I am well, and I'm very, very relieved to see that the James Webb Telescope got off the ground without a hitch and has unfurled.
Yes,
on its way to L2. So that's pretty exciting news.
It is great news. That's right. I mean, I think there have been several nail-biting moments, not just the launch itself, which I did watch live, but the unfurling bits, the unfurling of the solar shield. The key thing apparently was getting the solar panels unfurled so that the telescope has power. But yeah, we're on the way, expecting to be on station in a month or so. Looking forward to it.
Yeah, I looked that up online. I missed the launch because they delayed it. And when I thought, oh, okay, they probably delayed it by 24 hours. No. So when I expected it to be launched, it had already gone. But I watched the replay. But I did look up the live telemetry, and that was exciting, just watching the numbers tick over as it travels. I love that stuff.
Yeah.
I got that put in my car. So...
it is amazing stuff, that's right.
Yeah, it is. Anyway, we've probably got a lot to talk about in the coming 12 months as things develop with the James Webb Telescope, so we'll keep you posted.
Yeah, did you see the purported first image from the James Webb Telescope?
No.
It's on Twitter. No, so what it shows is it shows some words which are written backwards, and they say "remove before flight."
Somebody's having a go.
Yeah.
That's funny. I like that.
That's a nice one.
I like that. Speaking of first ever images, that little device behind me, I've taken my first astro photograph with a telescope and got a daytime picture of the moon, and came up all right.
Very, very good. The first astrophotograph I took was also with a telescope the same size as yours, a 3.5-inch telescope in the old measure, and also of the moon. And it was pretty rubbish, but you could see the craters. That was Andrew, in April 1962.
Oh boy, yeah. 59 years later, I got mine. You know what really confused me, Fred? When I got the box, I went, "Hang on a minute. It's supposed to be a 3.5-inch telescope. This is about 1 metre long."
Yes. Well, in the 19th century, telescopes were measured by the length. William Herschel talks about his 20-foot telescope and his 40-foot telescope.
Wow.
And that was the length of it. Exactly.
Now he's just showing off.
Yeah, he was showing off. Yeah.
Yeah, we could talk about telescopes all day. And
we could,
you showed me one a minute ago that's how old?
Oh, 200 years old, yeah. That's
200 years old, and Fred picked that up at an op shop when it was brand new.
Quite so.
Yeah, that's a real ripper. Okay, let's get down to business, as I tend to say. And they've been looking into this. It's actually a long mystery. This has been going on for a while, wondering about why certain comets have a green head, but the tail isn't green. And now it sounds like a pretty simple thing to try and solve, but this has actually been going on for a very long time, and I think they've finally cracked it.
Yeah, they have. So it's quite topical, Andrew, as well, because we've got Comet Leonard in our skies at the moment, which I have not managed to see because we've had such rotten weather here in Sydney.
Same here, and now I understand the frustration astronomers have with the weather, because I've wanted to get out there every night to have a look at this, and I can't.
Yeah. I think it's still visible. It's probably getting slightly fainter because it's moving away from us, but it's still not at its brightest in terms of its proximity to the sun. It'll get even brighter. So to the story, though, and it's some of the photographs of Comet Leonard that have been on the web clearly show the green colour of its coma. And just to get the technical terms right, the comets are basically dirty icebergs or icy dirt balls or dirty ice balls, whichever way you want to have them. They're made mostly of ice and dust. And they're only a few kilometres in diameter, the nucleus of a comet. But then when it gets near the sun, the ices start outgassing. They basically turn into vapor, and that causes what's called the coma, which is the fuzzy region around the head of the comet. And then those gases are driven away from the comet by the radiation pressure of the sun, so you get a tail. In fact, often comets have two tails. One is what's called the dust tail, and the other is the plasma tail or the gas tail. The dust tail is usually sort of neutral in colour, whereas the plasma tail sometimes does have colour in it, but it's never green, and that's what's what this story is about. So that, as I mentioned, the coma of the comet, and we've seen this with Comet Leonard, often has this greenish colour in it, but that disappears as the gas moves into the tail. Trailing actually not exactly behind the comet, it's in the comet, the direction opposite the sun, because the trails the tail of a comet is not always behind it. It can be in front of it as well. But it always points away from the sun. So there is a theory, or there has been a theory proposed 90 years ago in the 1930s by a physicist called Gerhard Hertzberg, and he suggested that the greenness comes from something called diatomic carbon, which is two carbon atoms stuck together, C2, which is something that we don't find on Earth because it's an unstable molecule. But he theorized that green color comes from the diatomic carbon, and you can kind of gather that from the spectrum of the comet, which is rich in green. However, that disappears, and he theorized that what was happening was that the sunlight falling on these molecules, these carbon molecules, was actually enough to dissociate them. In other words, it splits them into single carbon atoms. And that was the theory, but it's never been tested because diatomic carbon, or sometimes called dicarbon, is not stable on Earth and very hard to test. So, cut to the chase, this is an Australian story because it's been done in Sydney by scientists at the University of New South Wales, in fact, led by Timothy Schmidt, great name in astronomy, who's a professor of chemistry, and he's the senior author in this study. So what they've done is confirmed it. So they've done experiments which involve vacuum systems and lasers and a lot of high-tech 21st century equipment that essentially mimic what is thought to be happening. And so what it does, they use a vacuum chamber and essentially make the molecule C2 by actually what they did was they took a a bigger organic molecule, something called perchloroethylene, whose formula is C2Cl4, 2 carbon atoms, 4 chlorine atoms. And basically they used a laser to strip off all its chlorine atoms and leaving behind diatomic carbon, the C2. And then they sent that down the tube in the vacuum chamber to the other end and essentially flooded it with ultraviolet radiation, which is what the sun does, and observed that this tears the dicarbon atoms apart. And basically gives you the single carbon atoms, which don't form a green glow when they're excited. And actually, they also managed to measure the strength of this carbon bond, and that's. So it's quite a complex experiment, but basically what it has done is confirmed that Hertzberg's theory was exactly correct, even though Hertzberg himself had no access to any kind of way of physically testing this stuff. The lead author on the study, I beg your pardon, is not Timothy Schmidt. He's the senior author, but the lead author is somebody called Yasmin Borsovsky. Is actually a former UNSW honours science student, and one of the things that she says is it's incredible that someone in the 1930s thought this is probably what's happening, down to the level of detail of the mechanism of how it was happening. Yeah. And then 90 years later, we find out it is happening. It's a very nice quote. So the story is then that when these comets get near the sun, some of the organic molecules, and these are things probably like methane and molecules of that sort, which we know are in the ices of the comet. They get blasted by ultraviolet light from the sun, which forms the diatomic carbon, which glows green. But then as they get further away from the comet and perhaps the gas pressure around them declines, the further ultraviolet action from the sun splits the diatomic carbon into single carbon atoms, and the green disappears. So really nice story with some good experimentation to actually demonstrate what's going on.
Yeah. Yeah, the University of New South Wales, of course, one of the most esteemed universities in Australia. So, nice feather in their cap.
It is indeed, and I'm very proud to be an honorary professor in the University of New South Wales, but I contributed absolutely nothing to this work except talking about it on Space Nuts. So there you go.
Well, that's fair enough.
It's fair enough, yeah.
Yeah. Now, you did mention that sometimes comets have two tails. I believe Comet Leonard has sort of made the news not only because it appeared, but it has an unusual tail, does it not?
It does, and it's got structure in it, which is coming from what you might call outburst events on the nucleus. So you get, perhaps for whatever reason, you get a sudden burst of activity. There's perhaps the sun warms up a patch of the comet surface, and this is the icy surface, and you've got a region below where a cavity is formed in the ice, and that the pressure in there actually gets high enough to blow off the thin icy layer that's covering it up. And so what you get then is a cloud of gas being released by the comet, and that gradually works its way back through the tail of the comet, and so you see these features in the comet's gas tail. And there's been one that's really quite extraordinary because it looks like a finger pointing upwards. I don't know whether you've seen that one, but it's the effect of one of these gassy outbursts. It just looks like the finger of God pointing upwards. Very, very emotive stuff. Especially at Christmas time, Andrew.
Yes, indeed.
Yeah.
No, I just thought it was fascinating that they noticed these anomalies with Comet Leonard.
Yeah,
and of course, I suppose that also adds weight to the risk of it breaking up. That's one of the things they're worried will happen with it.
That's correct. That's right.
So far, so good. Hopefully, it'll survive long enough for you and I to take a peek.
I hope so. Yeah, I'm hoping for clearer weather tonight, but it's still raining at the moment.
Well, it looks pretty good here. We've got blue skies, but we've been having sort of late afternoon storms build up and cloud cover, and that sort of just kills everything. And the sun's not setting here till around about 9 o'clock. So you've got to be really patient this time of year.
and I'm the comet's setting not too far after that as well.
That's exactly right. The window is very narrow. Okay. You're listening to Space Nuts with Andrew Dunkley and Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, of course, from week to week, I rabbit on about becoming a patron. And, of course, that is optional and something you can do through our website, spacenutspodcast.com or spacenutz.io, and just click on the supporter link. And, if becoming a patron and making monthly contributions to the show is something you want to do, that is great. You can also just click on the Buy Us a Cup of Coffee link, which is a one-off donation type of an approach. But if you're not willing to spend money, that's fine. However, you could do us a favour by leaving a review about Space Nuts on your favourite podcast distributor, whoever you listen through, whether it's iHeartRadio, Google Podcasts, Apple Podcasts. I'm told, and we've never asked for reviews before, but I'm told if you do leave a review, it does get us more attention, therefore increases our audience. And with increased audience, there's, I don't know what happens. But anyway, more people are listening, and that's what we want. Now, if you listen through Spotify, up until now, you haven't been able to leave reviews, but that has changed. So if you listen on Spotify through an Android device, it's getting a bit more complicated, you can leave reviews for Space Nuts or any podcast for that matter. So if you would like to do us that little favour, that would be greatly appreciated, and hopefully that will lead to even bigger numbers and maybe some more friends on the Space Nuts podcast group on Facebook. So who knows, you might meet some nice people as a consequence of giving us a review. So there it is. Totally up to you, of course. Now, Fred, let us go on to this next exciting story, and that is, and I suppose this is a story where, like the previous one, we thought this situation existed. We ended up proving it 90 years later. Well, this is a situation where, and I think I said to you, do exoplanets likely have magnetic fields and things like that? And you said, yeah, probably. Well, now they've actually proven it.
That's right. Yeah, it is an exciting story, and it does have it's got kind of synergies with what we've just been talking about, because carbon is the key diagnostic that's been used here. excuse me, to demonstrate that an exoplanet has a magnetic field. And I should mention this work there's a number of different nationalities and institutions involved with it, including the University of Arizona Lunar and Planetary Laboratory. That's one of the great institutions for planetary studies in the world. But there's also the Astrophysical Institute in Paris, which has I think the lead author is actually from the Parisian group. But anyway, it's a multinational task, and that's fitting because it's a global thing that they're talking about, global in the sense of being another world, not ours. So what has happened is the Hubble telescope has been used to observe a known exoplanet, which is called HAT P11b. The HAT project is I've forgotten the exact name for the acronym, but there's one of the telescopes is at Siding Spring, and another one is in La Palma in the Northern Hemisphere. It's a project for discovering planets that transit across the face of their parent stars. The transit method, which we've talked about many times, where the light of the parent star dims slightly and reveals the transit of a planet going around the star. And one of the really clever things that you can do if you've got a sensitive enough telescope, and the Hubble is one of the most sensitive telescopes we have available, and certainly in the waveband that this work has been done, which I'll just mention. It's in the ultraviolet waveband rather than visible light, and that's basically a province unique to the Hubble. When Hubble dies down, we won't have any way of looking into the far ultraviolet until another space telescope comes along, because James Webb, of course, is at the other end of the spectrum. It's looking at the infrared signature of objects. Anyway, by observing HAT P11b in ultraviolet with the Hubble, what you can do is you can watch what happens to the spectrum of the star. Remember, you can't see any details. All you can see is this point of light, which is the star, whose light dims when the planet passes in front of it by a slight amount. But you can also look at the way its spectrum changes as the planet passes in front of it, because there's a tiny change in the spectrum of the star. And by that, I mean, the signature of the gases that are in the star's atmosphere. That changes because you've got imprinted on it the signature of the gases that are in the planet's atmosphere. Only a tiny amount, but enough that can be detected. And what you can do is subtract out the star's background spectrum, and you're left with the spectrum of the planet's atmosphere. It's fantastic stuff. And requires great care in the observations, but it can be done. And that's what has now been done. With HAT P11b, the research that we're talking about actually observed the planet during 6 of its transits as it passes in front of the star, and what they detected was carbon ions. So carbon ions are carbon atoms that have had some of their electrons stripped off. And the fact that they are ions, that they've got electrons missing, means that they interact with magnetic fields. And so what has been observed is these carbon atoms, the stripped off carbon atoms, forming a cloud around the planet itself, which is essentially being shepherded, if I can put it that way, by the magnetic field of the planet. So what they're observing is a direct observation of this planet's magnetosphere, which of course proves that it has a magnetic field. It's a signature demonstrating the magnetic field of the exoplanet, and the first time it's been done. So that's really interesting work, but these scientists have done more, because what they've observed is the fact that this planet is quite close to its parent star. I can't remember how close. It's 1/20th of the distance from the Earth to the Sun.
Wow.
So it's close by, and that means it's in the full breeze of the solar wind that's coming from this star. Excuse me. And what that's doing is basically boiling off the upper atmosphere of HAT P11b, and forming what's called a magnetotail. Now, the Earth has a magnetotail. It's the region on the opposite side of the Sun where the magnetosphere is highly distorted by the Sun's magnetic field. This distortion, in the case of HAT P11b, is much more. In fact, it's the magnetotail is almost like a comet. It's actually material that is being stripped off the planet's atmosphere, and it's actually finding a very long magnetotail. The planet itself is a kind of Neptune-sized, or a bit bigger than Neptune. It's 8% of the mass of Jupiter. But these scientists have done more work on the atmosphere that suggests that the atmosphere is actually similar to Jupiter, more similar to Jupiter than Neptune. And so they think that that's a bit of a puzzle, that its atmosphere, even though it's much smaller than Jupiter, that its atmospheric constituents resemble Jupiter rather than Neptune. So astonishing science that you can get from just this transit of a planet across its parent star, the disk of its parent star.
Now, I've been trying to figure out what HAT stands for, and correct me if I'm wrong, but I think it was a project that started 20-odd years ago.
Yes.
The Hungarian Automated Telescope Network.
I think
Does
that's
that sound
probably
right?
right. Yes, I think that's right.
Because they've been searching for exoplanets, and they used the transit method, and apparently they used initially, I don't know if it's still the same, but 6 small, fully automated HAT telescopes.
Yep.
And their work has proven quite successful. I think they've found quite a few exoplanets over recent years using the system called
that
HAT.
array. Yeah.
So hats off to them.
Very nice, Andrew. And, that's kind of paved the way. It was Kepler that showed how powerful the transit technique is for discovering exoplanets. And projects like HAT recognize that you can use smaller telescopes. If you put them on good sites, you get pretty good, photometric accuracy. That means the accuracy and the brightness of the star, and that has led to amateur astronomers being able to do this sort of thing with small telescopes. So who knows, that little telescope of yours might one day be discovering exoplanets if you really get your act together, Andrew.
Yeah, I'm likely to go, oh, I found a planet. Oh, hang on, that's Earth.
Yeah.
But someone else will probably have to tell me that.
Yes, that's right. But it's kind of moved into the realm of citizen science. It's great stuff.
Yeah, it's fantastic, and modern technology and the internet and the ability from people in their backyards to take astro photographs is just really opened things up incredibly well.
Yeah,
I was amused when I read the Hungarian Automated Telescope Network project when we were trying to figure out what HAT stood for. And it's just prompted a memory in my stupid brain because I retain useless information, Fred. We should not be surprised. We should not be surprised by how progressive Hungary is as a nation. And it sort of doesn't get – if people ask you to name the top 20 astronomical nations in the world, you wouldn't think Hungary. But they were also, wait for it, the first nation to mass produce perfume.
There you go.
I'm not kidding. Queen Elizabeth, not the one we know, but Queen Elizabeth of Hungary was the first one to commission perfume to be mass produced, and it was called Hungary Water. Not kidding.
There you go.
Don't ask me how I know that.
No, and I won't.
Of course, the Egyptians invented perfume, but Hungary was the first country to mass produce it.
There you go.
And look at it today. It's like a $44 billion annual
I'm sure it is,
global industry.
Yeah.
Amazing. I don't know how we got onto perfume, but anyway, I was hungry for information.
Oh,
there we go.
Andrew. I thought that might come up somewhere.
It had to, didn't it?
Yeah.
It had to. All right. We'll take a break. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, if you spend a lot of time online, of course, you can visit us on our website, spacenutspodcast.com or spacenuts.io, where you can send us messages or send us questions in text or audio form. You can visit our shop, of course, do whatever you like, except hack us. We don't really like that. But then you could also, if you're a social media follower, follow us now on Instagram. Spacenuts.io is our handle on Instagram. We're building up quite a following there now. And a few people have actually messaged us to say, yeah, you're finally here. I can follow you. So, yes, we're on Instagram, spacenuts.io, if you'd like to look us up and follow us on Instagram. And the reason I mention that is because we have a question from Instagram, Fred.
Oh, that's interesting.
Yeah.
Oh, it's Insta
An
interesting.
Insta question,
Yes.
which came to us instantaneously. This one's from Justin. He said, "Hey guys, love the show." Oh, that's one. I was wondering about cryostasis for long-term space travel. Do you think it would be a viable option? Also, what do you think the health implications would be? Thanks for your time, Justin from Tennessee in the United States. Thanks, Justin. Lovely to hear from you, and thanks for finding us. So cryostasis, you do see this in all sorts of science fiction shows. It's a way of stopping the aging process and putting the body into a sort of a long-term slumber so that you can travel long haul without dying before you get to your destination. That kind of thing. Viability-wise, I have my doubts.
Yeah, it goes back a long way, as you've said. And in fact, my first encounter with cryostasis, although it wasn't called that, was when Dan Dare, in the Eagle comic in 1955, he went to a planet called Kryptos, which was, I think, 5 light years from Earth. And in order to do that, they were basically frozen in these, what were called susper cells. Susper meaning suspended animation. So Dan and Digby and all the crew climbed into these things and basically slept for 5 years or something while they got there at nearly the speed of light. So it's a concept that certainly, as science fiction writers, have loved it. I mean, that's a long time ago, 1955, for Frank Hampson, who created Dan Dare, to put something like that in it. And certainly, there's scientific backing for the idea that you might do that. And in fact, haven't we got people who've actually had their brains frozen so that, when
in the hope that one day they'll be able to be reanimated.
Yeah, and sewn onto somebody else's body and carry on. So, as I always do, and I acknowledge my indebtedness to Wikipedia, which is pretty good at this kind of thing. That's where I went to try and get the formal definitions. So the term cryostasis was introduced to name the reversible preservation technology for live biological objects, which is based on using clathrate-forming gaseous substances under increased hydrostatic pressure and hypothermic temperatures. So that means you freeze things, but you immerse them in this clathrate-forming gas. What's a clathrate? It's a sort of chemical substance which has a lattice of molecules that can trap and contain other molecules. That's basically what the word means. So the idea is you've got these gases that you immerse the target object in, that form clathrates, that form these lattices that stop the dehydration of the atoms of the body or whatever it is when you get down to these very low temperatures. So that it's a way of stopping the dehydration. So the science of it is established, but whether you'd want to do it to a human and whether you'd want to do it for space travel is a very different question. My guess is that there might well turn out to be some gotcha that would not allow this to happen. I mean, the technology to do it with a human body is not there yet, or else people would be doing it all the time. To sort of go to sleep for a long time and wake up when whatever it was that killed them or was going to kill them could actually be fixed. That's still technology of the future. But as I said, that my guess is that, when you mix it with spaceflight, is it going to work? I doubt it. But I don't have any really justifiable scientific reason for saying that other than being cautious, which most scientists are. But I suspect there are problems. But what a great question, though.
Oh, it's a good question. Yeah. It does happen in nature in some respects. There are frogs that live in Alaska that can freeze solid for 7 months at a time, and their heart stops beating, but they don't die.
Yeah, and there are our little friends, the tardigrades, which can dehydrate themselves. That's how it works, and it's a different process from cryostasis, but they've got a means of dehydrating themselves. They turn into a little ball. If I remember rightly, it's called a ton. I might have that wrong. I can't remember. These tiny balls, because the tardigrades are creatures that are about 0.5 millimeter to 1 millimeter long. They are animals rather than microbes, but they've demonstrated that they can survive on the outside of the International Space Station by doing this dehydration. So yes, it does work in nature, but whether it could be harnessed for useful spaceflight, I'm not sure. And the alternative, for long distance spaceflight, and we're talking hundreds of thousands of years here, is to build big enough spacecraft that you can have multiple generations of people growing up and living their lives on these spacecraft to send a future generation to orbit Proxima Centauri or whatever to see what's happening. Yeah, it's the tyranny of distance that we've got in the universe, Andrew. It's going to lead you to these extraordinary solutions, which are really the only ways we could think about traveling these distances at the moment. Yeah.
I'm banking more on us finding a technology to create wormholes for long-haul travel or something like that, rather than sleeping it off.
Yeah, that's right. Yeah.
But, not in our lifetime, I wouldn't think. But, thanks for your question. Lovely to hear from you, Justin. Let's move on to our next question. This comes from Vinicius, I believe, in Brazil. Thanks for a great show. Good balance of information, humour and stuff. We're very key. Stuff is the key.
It is.
I am new to the show, and I've tried to find the 2 questions below in previous episodes, but I couldn't find them. So if we've already done them, don't worry about the question. Well, we're going to do it because I don't think we've really focused on this exclusively. So the first question from Vinicius is, how could a body emit gravitons constantly without losing energy, mass, or momentum? And the second question, which sit back and relax, Fred, this is a long one. The gravitomagnetism has been confirmed through experiments, for example, the Gravity Probe B satellite. A published paper has demonstrated that the use of a general relativity-based model, including the effects of gravitomagnetism instead of Newtonian-based models, can relieve the use of dark matter models for galactic rotation curves. Some studies with collected data from telescopes have failed to find the dark matter. What would be necessary for the dark matter theory to be replaced by gravitomagnetism or frame dragging to explain the extra gravity in the universe? Thank you in advance. Keep up the great work. Thank you, Vinicius. A couple of good questions. We'll go with the first one first. How could a body emit gravitons constantly without losing energy, mass, or momentum?
Bodies are essentially, they are losing energy. The way to think of this is, and I'm kind of doing this in my head at the moment, but we know that when high intensity gravitational waves are created, which is another way of talking about gravitons, by a collision between black holes and neutron stars, for example, or black holes and black holes. I mean, we've observed this already in measurements made by the LIGO gravitational wave detector, that you get a collision between 2 objects and they merge to form, so suppose it's 2 black holes, they merge to form a much higher mass black hole, but the mass of the black hole that's formed is not equal to the sum of the masses of the 2 black holes. There's a deficiency, which is interpreted as the loss of mass that goes into generating this huge gravitational ripple that's formed, the gravitational waves that are formed, and that all the sums sort of add up in that. So what you've got is a turning of mass into energy, and it's gravitational energy, so that's gravitons. So there is a mass loss in this extreme situation, and the bottom line is that there will be a mass loss in a normal gravitational situation, but the mass loss is tiny because of E equals mc squared. The energy that's created, if you think of energy being radiated, the amount of mass that change that works out as is infinitesimally small. I'm not sure that answers the question, and I think I might be missing a couple of aspects of this. But the bottom line is that there certainly is a mass loss when you've got a large gravitational disturbance created, which is what is happening with these collisions. And so the other side of it, this is really interesting stuff that Vinicius points out. The idea of gravitomagnetism, which has been confirmed through experiments with the Gravity Probe B, which was one of a number of gravity sensing experiments that were launched probably 20 years ago. Gravity Probe B, if I remember rightly, had a gyroscopic sphere spinning, which was one of the most perfect spheres ever made, and detected what's called frame dragging. It's the relativistic phenomenon, where a rotating body, and in this case it was the Earth, actually detects the rotating body drags space-time around with it, if I can put it that way.
I do think we touched on that.
Yeah, we did. Yeah,
a while back.
It was a long time ago.
Yeah,
but that frame dragging, which apparently is a confirmation of gravitomagnetism, or sometimes called gravitoelectromagnetism, and it's because of that it's sometimes abbreviated to GEM, which is a nice acronym. It's not quite perfumes, but it's jewels, which are the same league, and it comes about. What's gravitoelectromagnetism? It's where you compare the equations for electromagnetism, which are actually James Clerk Maxwell's field equations, and compare them with the Einstein field equations of relativistic gravitation, or usually known as general relativity. So you've got this almost a trick of looking at gravity as an analog. Looking at electromagnetism as an analog for gravity, but it has interesting consequences because you can link it to something we've just been talking about in a different field. That the kinetic effects of electromagnetism are how that if you get magnetic effects, if you've got a moving electric charge, then you get magnetic effects. And in the same way, magnetism actually limits a moving electric charge of forming a magnetosphere, which is what we've just been talking about, Andrew. And so it's a way of looking at how moving objects in a gravitational field, how that gravitational field affects them. And as I said, it was, as our listener has said, it was demonstrated by Gravity Probe B. Now, if you do the trusty thing and go and have a look at this on Wikipedia, you wind up with some really interesting but quite complex equations, but which do demonstrate those similarities between electromagnetism and this gravitoelectromagnetism. Whether it's so at the outer edges of this theory, you've got some really quite provocative ideas, which may well be helpful in understanding the universe. I'm choosing my words carefully here because it's a region where you can form analogies, but you can take them too far, if I might say that, and so they don't work. But scientists as eminent as Roger Penrose have actually used these GEM ideas for looking at the kind of frame dragging effects that you might get from rotating black holes. And apparently this Penrose mechanism has been proved quite rigorously. So there's all sorts of really interesting stuff that comes from gravitomagnetism, and there are still experiments going on at the moment as well to try and look at some of these phenomena. Whether it can explain dark matter is an interesting and provocative idea, how you can link these two together. And that's something I confess I haven't looked at, but will do as a result of this question. And maybe next time it comes up, I'll be able to give you a slightly more coherent answer rather than the garbled ramp through gem that we've just heard.
Well, we love the garble.
Thank you, Andrew. You've just made me feel heaps better.
Just doing my job.
Doing your job.
But no, great question and very thought-provoking. And as we try to resolve this mystery of dark matter, all these kinds of theories are going to sort of come up. And I love the way our audience comes up with ideas and thoughts sometimes and tosses them at us and says, could dark matter actually be mustard? I spill a lot of that stuff. But it's good. It's good. And thank you, Vinicius, for getting in touch with us. And thanks for finding the show too. We always welcome new people on board. Tell your friends, tell your mum. And don't forget, if you do have a question or a thought or a comment for us, you can send it to us via our website, spacenutspodcast.com or spacenuts.io, and just click on the AMA tab at the top, and that's where you can find the text or voice message interface and go from there. It's pretty simple. Fred, that brings us to the end of the last show of the year.
Yes,
Wow.
It is. Yeah, that's right. 2022 looms large on our horizons. Next time you and I speak, it will be indeed 2022.
It will be, and we look forward to it, and hopefully it'll be a much, much better year than it has been this year and the one before, but who can tell where we're headed?
Exactly.
It's been a time in our lives that I guess will be talked about for years and years to come, and even long after we're gone. But let's hope we can get past it real soon. Mm-hmm. Fred, it's been a pleasure. Thank you so much. We'll talk to you next week or next year, whichever comes first.
Sounds great, Andrew. Take care. And you have a happy new year. And if you're in Scotland, a happy Hogmanay.
You too, Fred. Thank you so much. Yeah. Professor Fred Watson, astronomer at large. And from me, Andrew Dunkley, thanks for your company. Nice to be able to share our thoughts and Fred's knowledge with you, and keep those questions coming in. And we'll talk to you again on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.
Okay.